Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next problem. Problem number 17. Okay. Fluid mechanics, problem number 17. As usual, we first come to our statement. Calculate the absolute pressure at the bottom of a freshwater lake at a point whose depth is 27.5 meter. Assume the density of water is 1.00 into 10 raised to the power 3 kilogram per meter cube, and that the air above is at a pressure of 101.3 kilopascal. Okay. What we have to do? We have to calculate the absolute pressure. Dear students, here one thing is to be noted that this portion that assume the density of the water is 1.00 into 10 raised to the power 3 kilogram per meter cube, and that the air above is at a pressure of 101.3 kilopascal. These two quantities are constant, okay, physical constants, which are usually given in tables given at the end of a textbook in appendix. Okay. So even if these two values are not given, we can see these two values from the respective table. Okay. That is table of densities and table of conversion factors regarding pressure. Okay. First I come to those two tables in which these two values are given. Okay, that is density of water 1000 kilogram per meter cube and standard atmospheric pressure, that is 101.3 kilopascal, or 1.013 into 10 raised to the power 5 pascal. Okay, now first I move forward. This is the first table. Here you can see that 1 atm is equal to 1.013 into 10 raised to the power 5 Newton per meter square. 1 atm is equal to 1.013 into 10 raised to the power 5 Newton meter square, Newton over meter square, which alternatively becomes equal to 1.013 into 10 raised to the power 5 Pascal, which alternatively becomes equal to 101.3 kilopascal. Okay, so this value that is in shape of kilopascal is given in this statement. Okay. So even if this value is not given in this statement, we can find this value from here. Okay. Now we see the other value. This table again is about this similar situation in a slightly different manner or mode. Okay. This table is also relevant to some extent. This is the table of densities in which at left column at serial number 5 density of water is given as 1.00 into 10 raised to the power 3 kilogram per meter cube. Okay, in other words 1000 kilogram per meter cube. Okay, so these two values, density of water and value of absolute atmospheric pressure, even if not given in this statement, we can find these two values from respective tables. Okay, so now we come towards part B. Okay, what force is exerted by the water on the window of an underwater vehicle at this depth if the window is circular and has a diameter of 35.0 centimeter? Okay, dear students, what we will have to do here, diameter is given, but actually as per formula for calculation of area, we are concerned with radius. So what is radius? Radius is half of the diameter. Moreover, we have to take radius in terms of meter instead of centimeter. Okay, so its radius will become 17.0 centimeter, and when it will be converted into meter, it will become 0.175 meter. Okay, quite easy. Now we come toward the solution. We know that the pressure in a fluid at rest varies with depth h in the fluid according to the expression P equal to P naught plus rho GH, equation number 1. Okay, where P naught is the pressure at H equal to 0 and rho is the density of fluid assumed uniform. Okay, because density is always uniform and is a constant. Okay, so using P naught equal to 101.3 into 10 raised to the power 3 Pascal and rho equal to 1000 kilogram per meter cube. Okay, both these values are given in this statement. Moreover, value of G, acceleration due to gravity, is also a physical constant, and we know this value from very earlier classes. Okay, from about 8th class. Okay, acceleration due to gravity 9.8 meter per second square, and height or depth. Okay, height or depth are equivalent terms. Okay, so this is given as 27.5 meter. Okay, moreover, according to table of conversion factors, we know that 1 Pascal is equal to 1 Newton per meter square. This alternatively becomes equal to 1 kilogram per meter second square, and this alternatively becomes equal to 1 joule per meter cube. Okay, here we are not concerned with this last equivalent value. Okay, we are concerned only with the first two equivalent values. Okay, so using all these values in equation number 1, we get. Dear students, here before proceeding to next step of this problem, I come to the point that in solving problems given at the end of a chapter of textbooks of physics, we are primarily concerned with data provided in the statement. Okay, and this data may be divided into 3 categories. Okay, number 1, data which is expressly given in the statement. Number 2, data which is required to be determined in the statement, and number 3, data which is not provided in the statement but it is provided in the table of physical constants in appendix at the end of almost all textbooks of physics. Okay, what I have said? I have said that while solving problems of physics, We are concerned with three types of data provided in the statement. One type of data is expressly provided in the statement. Second type of data is that which we are required to calculate, which we are required to find at the end of the solution of that problem. And third type of data is we can say that it is impliedly or implicitly given in the statement. That is to say that data is relevant for the purpose of determining our solution, but that data is not expressly provided in the statement, and we have to consult tables of physical constants and take that value from tables. Okay, for example, here this is acceleration due to gravity is a constant which is given in the table of physical constants. Similarly, this conversion factor is given in the table of constants. Similarly, these two values, despite the fact that these two values are expressly provided in the statement, even if these two values are not given, these are given in the concerned tables. Okay. Now, dear students, P becomes equal to this plus this. Okay. So, what we are going to do, we are just going to simplify. Okay. In place of Pascal, we have used kilogram per meter second square. Okay. So, here kilogram 1 meter will be cancelled from these three power, and here meter square will be left, and this from here 1 meter once again be cancelled. Okay, that is m and m square will be subtracted and simply m we will get. Okay, so kilogram per meter second square, here again Pascal is also equal to kilogram meter per second square meter second square. So we can take common factor as this value from both these and add these two values while simplifying, and hence that is to say we get P equal to 370,800 Pascal, or alternatively we can write it as 3.708 into 10 raised to the power 5 Pascal, or we can also write it as 370.8 into 10 raised to the power 3 Pascal, that is kilopascal. Okay, so our part A is solved. Now we come toward part B. We know that the pressure P in a fluid is the force per unit area exerted by the fluid on a surface. Pressure is defined as force per unit area. Okay. Equation number 2, here once again we have many times shown this table, okay, in which it is emphasized that equality or these horizontally three parallel lines are almost equivalent and convey the same sense in mathematical expressions. Okay, so here area is calculated as pi r square. Okay, we know that area of a circle is pi r square, where area of a sphere is 4 pi r square. But here we are concerned with area of a circle, not with area of a sphere. Okay, a value of pi is 3.14, which we have already mentioned many times that its decimal representation is non-terminating, non-repeating, but we have restricted its value only to two decimal places, that is pi is equal to 3.14. Okay, moreover we have obtained radius r by dividing decimal diameter by 2 and then converting it in meter. So radius from diameter 35 centimeter has become equal to 0.175 meter. Okay, here P is that which we have calculated in part A of this problem. Okay. So here in place of P, we will use that value which we have calculated in part A. Okay. This value. Okay. 3.708 into 10 raised to the power 5. Okay. 3.708 into 10 raised to the power 5 Newton per meter square. Okay. So putting all these values, moreover this conversion factor will also be used. So, okay, so what we have done, we have simply put the values. So from here force will be kept on one side and this will be multiplied with this. Okay, so when it will be multiplied here, meter square will be cancelled out with meter square and we will be left only with Newton, and we know that force is expressed in Newton. Okay, so force will become equal to 35,657.055 Newton. Okay, to this extent our problem is completely solved and we do not need to go further. But as a matter of discretion, we have converted this value as 3.5657 into 10 raised to the power 4 Newton. Okay. Similarly, we can write it as 35.657055 into 10 raised to the power 2. No. If we convert it in 35, then it will become 3. If we convert it in 356.57, then it will become 2. If we convert it in as a 3565.7055, then it will be 10 raised to the power 1. And if we write it as in this form, then it will not be multiplied with 10. Okay. So our answer has become force equal to 3.5657 into 10 raised to the power 4 Newton. Now we come towards the reference book. Okay. Reference book is Physics for Scientists and Engineers with Modern Physics. Authors are Raymond A. Survey, John W. Jute Jr. Its publisher is Cengage and its 9th edition, having been published in 2014, has been adopted. And here chapter number 14 under title Fluid Mechanics is our concerned chapter. And this problem is enumerated at serial number 11 of the exercise at the end of this chapter. That is to say exercise number 14.11, and this is the end of our problem. Okay.